Right, Assalamualaikum and a very good morning. So today we are going to continue on our topic for the 80 mega architecture, architecture for 80 mega 328, the specific single IC microprocessor that we have chosen. Right. So let me share slides first. Screen. Okay. All right. Where did we finish off last? I think we finish off at interrupt. Yes, we finish off at interrupt during the previous session. So we are looking at the bits for registers. Let me see. Can anyone remember where did we finish off? Did we finish off everything for the whole bit? Or should I repeat for these registers? Okay, then I will repeat. All right. So we are looking at the status registers SR. The short form for status register is SR. Or you can also use SREC. SREC. Please do remind me if we have done this. Right. If not, I will just proceed to repeat again. Right. So we have our goal interrupt bit. All right, where it is a global interrupt. It is a global interrupt. And of course, we have specific interrupts. We have many interrupts for many functions. Here you can see here we have interrupt. We have interrupt from I/O. We have interrupt from analog comparator. We have interrupt from several other processes lah. All right. So the status bit here, the status bit I for this status register is the interrupt for to control all. Right. So if let's say an interrupt happen, so the I bits here will be set, will be cleared. So when an interrupt occurs, I bit here will be cleared. And then after you finish the interrupt service routine, and upon finding your instruction RETI, return from interrupt, this instruction will set this I back to its original state. You will put on sets again. All right. So that it will enable other interrupts to occur. So interrupts. So the what you call it? You might think that computers are parallel. So if you actually see your Arduino, everything is being done in sequence. It's not totally in parallel, except for certain features, right? For example, that do not need any programming, right? Things like the watchdog timer, right? Things like your watchdog timer, maybe some power supervision where you do not need any specific programming. It might be monitoring in parallel, right? But basically, your program that you put in your Arduino or your 18MegaTree or any other microprocessors, they are executed in parallel. I mean, they're executed but in sequential, in sequence. All right. So the thing is about interrupt is that uh, you as programmers or engineers, you will need to define which task is not which task is important, which task is critical, and which tasks are not. Right. So usually interrupts uh, is some processes that is much more significant and important, maybe important in terms of time, or maybe important of the sensor status, sensor measurements, right? So compared to the main program or the main loop of your microprocessor program. Right, and these interrupts they have although you have many interrupts, so you cannot service many interrupts at one time. And when an interrupt is being serviced, is being serviced lah, right? When the control has been passed from the main loop to one interrupt service routine, right? Other interrupts cannot interfere. Alright, that's why later you will see in our topic interrupt, even the interrupt have priority. So you can arrange which interrupt is the most important. Let's say you have suddenly two interrupts are triggered, right? For example, right? Who knows? Because the interrupts are taking measurements from other sensors or from, so there's a possibility that those interrupts can happen at one time. Yeah. So and then you need to define before that um, your interrupt priority. Which one of all the interrupts is the most priority? Which one is the second priority, and third, and so on and so forth, right? But again, I would like to emphasize here that your interrupt, your program is basically sequential, right? Uh, of course, we have parallel processing, parallel program. Parallel processing microprocessors. Yes, we do have, but that would usually cost you more, right? That would be your for example, your core, your phone. For example, your phones, you have your dual core, quad core, octa core, 8 cores. So all those cores are processing in parallel. So tasks are being divided in throughout the cores, and the cores are processing that in parallel. But the processor that we have learned, in our course here is done in sequential. Alright, and after you have finished the interrupt, okay, let's say you don't want to receive any more interrupt. Alright, then you can clear through your program. Let's say after certain process or after certain conditions, you don't want your device to receive any more interrupt. So you can use the instruction CLI. This is the one operation, clear interrupt. So this instruction will clear this bit over here and thus disabling your global interrupt. And let's say after some time or after some conditions you want to enable it back, then you can put the program the coding program here as using SEI and this will set your interrupt bit. So this status register as overall, you can see here it's written here RW. So which means that these bits, specific bits, can be read and can be written on. Right? You can read from the status. You might want to have a program where you need to read first the status. All right, then for you to do some decision in your program. Right, when it is high, for example, then you want to make it low, or if it is low, you want to make it high. So you can read this one first, and you can also modify this bit. So there are, you will see some registers later that it might be read only, all right, or it might be write only. Usually, not, we don't have write only lah. We can have read only, seldom. Right, and here below here we can see initial values lah. Right, so when you on your microprocessor, when it starts running, right, this is the initial values, right? So it is basically all zeros lah, right, all zeros. Okay, so that's on the interrupt bit in the status register. All right, and then we have our bit copy storage. All right, bit copy instruction, bit load. If you want to write a process, bit load lah, bit load. So from T is what? T is this bit you copy to a register file. So bit load, you copy this bit to a register file, or the other way around. You copy the bit from the register to this bit in T. So this bit in this T bits in the status register indicates the status of the bit copy storage. Right, so we have bit load and bit store. All right, that's the 6th bit. Now we go to the 5th bit, status register SR. All right, on H. So H, bit 5 is the half carry flag. So indicate half carry flag, indicate half carry in an arithmetic operation. So usually, if you still remember, your logic digital electronics or logic digital, right, you have processes called the binary coded decimal, BCD arithmetic. So in this process you have the half carry bits. So let's say you do some calculations in your program. So when so this one says here indicate. So it's not like you can write. Of course you can write to this bit, but mostly you need to read first, because this is an indicator, right? So you need to read first, or maybe you have some operation and then you want to look at the operation. Is the H bit, is there a half carry after the arithmetic operation? So if there is, when you read these bits, then it will be high lah. All right, so when there is a half carry. So this is very useful in BCD arithmetic. All right, and then you have the S, V, and N. So the sign bit depends on the status of your bit V and bit N. So you XOR, you do the process of XOR between the bit N and bit V. So what you do is you have to look at the N first lah. Right, the negative flag. N means negative. This indicates negative result in arithmetical and logical operations. Let's say when you do some arithmetic operations, let's say you can have something like 3 minus 4, right? 3 minus 4, so of course you will get the answer 1 with a negative sign. So when that happens, the bit N will be high. So when you read this bit, it is high, then you will know that it is a negative answer, right? So and then we have the V bit is the two's complement overflow flag. Two's complement. So you can use this, or you can read this bit to see if there's a overflow of the two's complement arithmetic. So to revise what's the two's complement, you need to look back at your previous note for your digital electronics. Right, so you have your N and your V, and then you will get your sign bit S, right? And And then you have your Z and C bit. So Z means zero flag, so indicates a result in arithmetic and logic operation. So when your process give a result of 0, so this bit will be high, right? Or if it is other than 0, then this bit will be low. So then you have your carry flag. So this indicates a carry in arithmetic and logic operation. So when there's a carry is involved after the process, this bit will be set high. So if there is no carry, this bit will be set low, right? So all these 8 bits, 0 to 7, I, T, H, S, B, and Z, C, right, were combined together to create some value lah. Usually you represent it as a hexa value. So for example, this is my notepad. Okay. Right. So all these bits, if you have a binary, so if it is a 0, it becomes like this lah, 0, 0, 0, 0, 0, 0, 0, 0. Right. So let's say you do a process and then it becomes your the resulting process from the arithmetic or logic bit is 0. So what happens is your S right will become something like this lah, right? 0, 0, 1, 0, right? And then if your result is negative, right? What will happen? Okay. So that is for the status register. All right. So that is the first register that we have looked. Right, so I've shown first the ALU, and then we started our registers with the status register, and then we proceed to discuss on the general purpose register file, which is this, right? So all registers, most including this status register is 8-bit wide, so 8-bit wide. So so when you talk about general purpose register, these registers is general purpose. It's not specific to any functions, right? In any functions from, let's say, the port or the analog comparator, or it is not from the interrupt. So these are separate general purpose registers. Right, for all other features which has been embedded in the ATmega 328, right? All these features they have their own registers. They have their own registers, right? And their registers have their own addresses. So what we're talking about here right now is about the general purpose register. So it's a general, right? So you can use this register to manipulate, right? So the reason you have this register is that it is not always that you want to, let's say you want to do some calculations, you want to have a small array to save data, right? Temporarily, let's say you have a process and a mathematical algorithm, you want to do some, you have some process and you want to save something else, then you do a second process, you save something else, and then you want to do some addition of the two resulting results to the first. I mean, you want to do operations on the two previous results from the two previous process. So you want to have a temporary place for you to store, to hold first, and then you can fetch that later, right? So so I have a question here. So is this in the RAM, SRAM? So is this general purpose register file in the RAM? Right. So this is a question for you to ponder with. So okay. So total we have 32 registers, 0 to 31, right? R0 until R31. All right. The thing is, you can treat R0s until R31, totally like general purpose register. On top of that, later we will see the X, Y, and Z register. It is also part of the GPR, the X, Y, and Z. The only thing is that, let's say you want to have some processes regarding using 16-bit wide, 16-bit wide. Therefore, built inside the architecture of the ATmega 328, you have the X register. So you have the X register low byte, and then you have your X register high byte. So total is 16-bit lah, right? Let's say I'll try to put this on Notepad. Okay. Okay. So let's say if let's say I want to ask you, where is the address of the register R17? So the address of register R17 is the address is at 0x11. So this is the address of the register 17, right? So if I were to ask you what is the register, I mean the address of register X, for example. So your register X is address. Usually when you arrange 2 bytes, 2 bytes, of course you have your high byte on your left, your low byte on your right. So in this case, high byte is in the address 0x1b, so that will be 0x1b followed by the address 0x1a, right? So that will be the address and arrangement. So this is the high byte. This is the high byte, and this is the low byte. The low byte. So that makes up 16 bits lah. That's total of 16 bits for the register X. Okay. Okay. So for this this okay, you can use again these registers. The range of address is from 00 until 0x1f over here, the address. All right. Register XYZ starts from 0x1e, and then the purpose I mean the architecture of the ATmega 328 allows you to do 16-bit process. So you have to look back at the instruction set, which instruction sets allow you to do 16-bit processes, right? So you have your operand, you have your opcode, your operation, and you have your opcodes. So you can, or if you use, I mean the XYZ register, you can have a combination of like something like this. You can have an output during your process. You have an 8-bit, one 8-bit, and then you have another one input. If you can have your input to have 8-bit, right? Or you can have your input one 8-bit, and then your resulting output can be 2 8-bits. Or you can have a process whereby you can combine two. You can have one process of one we call it operand, one operand with whose length is 16-bit. Then you can have outputs, two outputs of 8-bit, or the other way around. You can also have an input operand of one 16-bit, and then your output operand of 1 bit. So the architecture for the 80 mega has been designed to do this. Therefore, if it is possible for you to do this. All right. So this is the details on the XYZ in the GPR. So these XYZ registers are located in the general purpose register file, GPR. So you can see here, right, XH, and then your XL, your high byte and your low byte. So the address starts on the later part starts with 1B first and then 1A. And then there goes also for your Y register, you go for 1D first, then 1C, and your Z starts with 1F and then 1E. Right. Usually, these X, Y, and Z registers are used for 16-bit address pointers for indirect addressing of data space. Right. So usually addressing is usually 16-bit 16-bit. If you have 8-bit addressing, right? Let's say an 8-bit address, an 8-bit address would 8-bit address, right? Would starts from 0 until 255. So that's a total of 256 addresses. So this is very limited, right? For example, your RAM has, if you look at your 80 mega 328, all right, your RAM provided is 2 kilobyte, 2 kilobyte, right? So that would be around exactly around 2048 bytes, bytes. So this is 2 kilobytes. Usually, when you see 2 kilobyte, it is not exactly 2000, 2000, because when you talk about bytes, so it is kilos in bytes is, so if you say 1 kilobyte, right, that would be 1024 bytes, right? So 2 kilobytes means 1024 times 2. So that is the notation used, the kilobyte notation used by all these microprocessor manufacturers, right? Okay, and what we're talking about just now is that, okay, if it is an 8-bit addressing system, all right, you can only fetch up to the 256 addresses only in the SRAM, right? So if you want to reach for more, then you need more addressing bits in this case. So usually you multiply by, you do multiplications of 8 right? You cannot have things like of course you can have actually in microprocessors, but usually when you do programming you don't have things like 11-bit programming, right? So you don't have like 13-bit programming, but you can have 13-bit 13-bit address, physical address lines. 13-bit you can have 13-bit physical address lines. Yes, you can have that. But when we're talking about addressings, right? So it is always 16-bit, 8-bit, 16-bit, 8-bit, 16-bit, 32-bit, 64-bit. So that will be the addressing. So you can look at your computer, those that you have. You can right click on your Windows. You can look, is it a 32? Is it using the architecture for 32-bit or 64-bit? So if you want a faster processing, so you go for 64-bit. All right, so the reason, okay, here, 16-bit address pointers for indirect addressing. All right, yeah, in our addressing for, you want to address the memories, you can have things like direct addressing, right? You can have processes like indirect addressing. Indirect addressing means it is a pointer. It stores. Let's say this register, it does not store address, but yeah, it stores address, and that's why you call it the pointer. Pointer. But so when you have your operations, you don't need to write your exact address. You can just load from the pointer. I mean the register of X, for example, and then you can have um, a simpler instruction set, right? You don't have to write many times, right? Because when you do this in the addressing, you can have operations like fixed displacement, right? Fixed displacement, auto increment, or auto decrement, right? Without you having to memorize your addresses in your RAM. Let's say, for example, after you have set some processes in your RAM, you have done so many processes in your RAM address is what, let's say between 0 until 2047. Okay, you have addresses like 1560 or 1567, right? So you have some process starting from this address, right? But when you do programming, right, it is impossible for you not to look, okay, which RAM you have 200, you have 2000 spaces of RAM in your microprocessor, but you want to assign a new address, a new variable to your SRAM. You want to look for what address has not been used yet. We have 2000 addresses. You want to know which part has not been used, or which address is the last address that you have used, things like that. So it's impossible, right? And also if you want to increment, so you cannot, it is very hard for, you can do this lah, you can actually do this, but your coding will be very long. And if you want to troubleshoot later, let's say after you do some programming, of course you don't have syntax error, right? But your program does not work like you want. So for, and then that program is related to the addresses in the SRAM, for example. And then you have to trace on your own. You have to do some tracing, step by step, the address, look at which address has not been used yet. So that would take time for you. But when you have if you use this indirect addressing feature during your programming, you can have a fixed displacement. You can have auto increment or auto decrement. So just by, let's say, for example, things like you want to, let's say, so let's say in X, is already stored a certain address. So you want to displace after 512. So this, what will happen is that, but previously you have already started, you have already initiated your X with some address, right? Initiated with some address, for example, and then you want to displace. So you don't bother. Where does X comes from? You want to declare a new variable for a RAM, right? So you just displace from the address stored in X, right? But you don't need to bother to know the address of the X. So what happens is that if you have some the address, the final address is based on 512 added to this the address in the X. So because you want to, let's say for example, you want to allocate 512 addresses, but you don't need to know it starts from where. Pardon me. Okay. Yeah. Yeah. Nah. Boleh. Tak, ada kelas ni. Nak tengok sekejap tak apa dulu. Ah. petang.
Oh, nanti awak pilih machine. Have a look on the battery.
Okay, maybe afternoon kita.
So, based on our discussion.
Okay. Right. Where is it? Right. Pardon me. So you don't need to know where your X starts from, but you want to allocate 512. Right. So this is called displacement lah. Displacement. Or you want to have some process where you want to have a loop. For example, you want to increment. You can put something like this, for example, or you can have a decrement, something like this. Right. And later you will see you can have a process of post and pre. So this is pre-increment, then this is post-increment. There are instructions like pre-decrement or post-decrement, things like that. So you don't need to know the exact value where is the x, but you want to focus on certain processes, right? Specific to the numbers, specific to increment, things like that lah. Right. So this is one advantage of using this feature of indirect addressing of your data space. So remember again, what is your data space, right? So do you know what we are talking when we talk about data space, right? So this is a question from me for you to ponder with. All right. And then lastly, you have your stack pointer. You have your stack pointer. So the address of the stack pointer is at 0. Okay, what you can see here, if you look at this address, 0x5e and 0x5d. All right, it is not, this address is not within, it's not within your GPR, your general purpose registers. Your general purpose register starts from 00 until 1F. If you look at here, this is your data memory. All right. So again, this is data memory. Is it same to data space? So this is question for you. Right. So 32 registers. Right. This is GPR. And then this is your 64 IO registers. Okay. So this is what we are talking about. Your input output registers. This one is related to the built-in features inside your 18MeG328, and then you have another range of registers, which is the 160 extended IO registers, specific to certain functions lah. We will look at IO registers later. Right. So the question is, where is this stack pointer located? You can see here it is located at the address of 5E or 5D. So it is somewhere at the end of your IO register. All right. So you can see here all read and write, and you can see that the stack pointer it is a 16-bit. It is a 16-bit register. So it starts from 0 until 15. Right, the lower byte of your stack pointer starts from the address 5D, and then your high byte is at the 5E. 5E. So do you think it is the same? Right, C, D, E, C, D, E. So low and then high first. If we look at the X register, this is low and then high. Okay, it's almost similar lah. This is how 18MeG to it. There are some other microprocessors that you need to be aware of. Some microprocessors, they have the other arrangement of the other way around. For the high, they have the first address. They put high first. right? High and then low, right? But for 80 mega, they put low first and then high, low and then high, right? For 80 mega. So there are microprocessors where you have the high first and then low first. So you need to be aware. Let's say you were to use some microprocessor that your company gives to you later. Say, okay, we want this new processor that we have bought. So look up on the data sheet and see what type of architecture that microprocessor is using. Right. So even though in our course we use 80 mega 328, but we want to be open-minded here, right? We are not, you're not. Of course, we are learning specifically on 80 mega 328, but we need to be open-minded that this is this is the same things that you will look for if you were to use other microprocessors. The same thing. If you want to find other microprocessors, you open up data sheet, look at the instruction sets, look at the registers, look at the data memory, the memory map, things like that. All right. So stack pointer. Stack pointer is actually stored in your data space. Usually at the end of your RAM. So the initial value is stated here as is at the RAM end. RAM end. Right. So for example, 80 mega, the internal SRAM is here, 2048 times 8. So usually where you declare your or where you initiate, where you declare your initial address of your stack pointer is at the end of your RAM, usually. So that's the main practice that people have. Programmers have done that. So the stack pointer. So what is a stack pointer actually? Stack pointer is stores address. Let's say you have, remember you have your main program and then your interrupt service routine. Right. So the thing is, for example, you are doing in your main program. It is you are executing something. Something. If you do some operations on the RAM, then there will be no problem. If the operations on the RAM, there will be no problem because it is stored there. But let's say, for example, you have processors which use these 32-bit registers. I mean, 32 general purpose registers. You have R0, R1 until R31. So you have many operations in your main program that use all these registers. All right, for certain processors, for certain reason, for certain purpose, things like that lah. So depend on you programmers you want to use. Right, and then suddenly there's an interrupt. Right, an interrupt happen, and in that interrupt, you want to use the whole set. You want to use the whole sets of this general purpose register. But at the same time, you don't want the values inside the GPRs, when you do the main program, you don't want to lose them, those values. All right. Okay, this is what will happen. So what you will do when an interrupt happen in the midst of you processing, doing some processors within all these registers, right? And all the registers already have values inside, right? But suddenly an interrupt happen, and you want that after the interrupt finish, you want to continue the process, which means that you cannot lose the values inside these registers, right? But the thing is, when you do your interrupt service routine, all right, the what you call it, your interrupt service routine also wants to use the general purpose register, right? Maybe part of it or all of it, right? But at the same time, you don't want to lose the values inside your, I mean, the GPRs when you do that in the main program, when you use them in the main program. So what I do is you're going to push, you're going to push. So this is where, this is how your stack pointer is, you're going to use your stack pointer. So so usually at the beginning of your interrupt service routine, you need to put an instruction called push. Push. So data is pushed onto the stack. You just push, right? So other than so what will be pushed? What will be pushed? Basically, all these current values when you do in your, the current values of your GPR. All right, when you do your main program, right, all these registers will be pushed. Pushed where? Pushed to the RAM. Right, pushed to the beginning of the RAM, right, and at the RAM end. So it's push. It starts from here. So it will start storing uh, uh, from the end, from the bottom, R1, R2, R3, R4, R5, R6, R7 until R32. Right, so it push data. So it's like saving lah, right? It save all your values of R1 until R32 is saved in your RAM temporarily. All right, and then in after that, after you do the push in your interrupt service routine, then you can usually you want to clear lah. You want to, because your previous value of R1 until R32 has been saved in the stack pointer, right, in the stack. Now you can freely use your R1 until R32. So but before that you want to clear first lah. So you clear all your R1 until R32. Right, and then you can start use R1 and until R32 in your interrupt service routine. Right, and usually when you use that in the interrupt service routine, you don't store that much lah. You do some processes, and then you get a final value. But usually you don't store lah. You don't because you cannot have an interrupt, and then when you do one interrupt, you can, and then suddenly come another interrupt. So remember again, if you use in the status, the status register, the global interrupt. So when you are servicing one interrupt, you cannot have another interrupt happening. All right. So if you have another interrupt happening, now we have nested interrupt lah. So you need to again to save the GPR use into the stack again. But let's assume no nested interrupt will be happening. So you can use all the R1 and the R2, and then after you finish all that, okay, you will do the instruction. You call it pop, pop over here. So data is pop from the stack. So when you do this pop instruction, all right, all those GPR R1 until R32 that you have stored on the RAM, right, all those data will be passed back to R1, to R2, to R3. So it is something like a restore back all the values of R1 until R32. And then after it restores all your R1 to R32, and then of course at the end of your interrupt service routine, you need to have your instructions RETI, RETI. All right, and what you call it, right, RETI. So the control will be passed back to your main program lah. And then when you continue your main program, all right, you can continue your process and you can continue to use your R1 to R32 with the values inside them like normal, like nothing has happened. But you need to do all this process lah. You need to use the stack pointer, you need to push, then you need to pop, and then you need to return or RETI. RET means it is a return from subroutine or return from function, but this function is not from interrupt lah. So this you will use the same you call it the same notation lah. You need to use the same process, push and pop, and the stack pointer for both interrupt service routine and for both normal service routine, which is not from the interrupt, right? So what happens here? The stack pointer is it stores the address. So the RAM at the end of the RAM here, it stores the value. It stores the value of those registers that you have pushed and that you're going to pop after that. All right. But this stack pointer stores the address. So initially, right, this stack pointer will point to the address of, right, 08FF. So why 08FF? This is because if you look in the data sheet, the internet SRAM for 80 mega 328, right, is 2048, 2048, and the RAM at end address, the final address is 08FF, which means that your stack pointer initially is at 08FF for your 80 mega 328, right? I might ask you some questions which is a little bit off from the 80 mega today. I might ask, okay, if it is 80 mega 44, right? Yeah, 44. So it might the step pointer might be pointing at 02FF, right? So you need to be very aware of the question is given to you. Right? So step pointer starts from the end, right? Only when you pop, when you do the push, so you'll be the step pointer, the value inside the step pointer, because the what you call it a step pointer, it points to an address. So initially the value would be 08FF, right? 08FF. So 08 means 0000. 1000, is it one here? 124, yeah, 1000, and then 1111 throughout until here. Okay, so when you pop means you store one, you save one register. So when you save one register, your step pointer should point to the address before it, right? Because you start from the RAM end, and that's how step pointer works. Step pointer is basically it starts from the bottom and it goes backward. Usually when you do programming or you do your programming, you want to have you want to access your address from top to bottom, but step pointer is special. You start from bottom to top. So that's why when you save one value, the step pointer now will move to the previous address. Then you save another value, and then it will point to the previous address, right? So I think I will give you one question quiz after this to see if you actually understand this step pointer process. So when you pop, push is the opposite of pop. So when you pop, it will be increment by 1. So pop means you return this this value here to the actual register, let's say R1 or R2. So after pop out, you restore, the step pointer will go down because you have returned one value back to the GPR. And then you pop again, then it will increment again, goes down again until you finish popping, right? So you have no more registers that you have saved here. Then you can continue your program, right? So this is how push and pop. Okay, and then you also can have things like call, iCall, and rcall. Okay, the call is like when you remember when you do your programming, right? You have your if let's say for example your Arduino, you have your setup, It's a setup function. Right, where you do your C, right? Your C program, you have your setup. Below that, you have your main loop, right? And let's say if you want to have some functions that you want to repeatedly use, you can create your extra functions below, right? So in programming, in C programming, those are called functions. For functions, and you just call the function by, let's say for example, let me write here. Here, for example, you have your main program, something like this. Okay, void as a main, like this. Void main void, for example lah. Then you have your program, right? Program. It's like this. You have your program. Then you can call, you can create a function. Let's say your function is returns an integer, right? This function say a function is an addition, add and subtract, for example, add, subtract. So you have a program here, simple program here, which adds and subtract, for example. All right, and this is your function, right? So when you want to call it, how you call it, right? You're going to write this way, right? Remember, you're going to write something like this: add, then call subtract. This is in C lah. So this is called a function. For assembly language, they call it a routine. If this is called a function, if this is called function, function, right? And for assembly language, this is called right. For assembly language, for microprocessors, this is called routine. Routine, right? You can, so how do you for assembly language, you don't, how do you call a routine? This is called a function. You call a function. For assembly language, you will do something like this: call, add, subtract. Right? For assembly language, so you call something like this. For C programming, you will do something like this. Right? For assembly language, you will call that function something like this. So the thing is, your main program can call a routine, can call some subroutine. Okay, call it a subroutine. Call it a not routine, call it a subroutine. Subroutine. This is your main routine. Your main program is your main routine. Extra function is called a subroutine. Right. So you have your main program, right? Your main program. Suddenly you want to call subroutine, subroutine below that. Right. So the thing is, for we have not discussed on program counter yet, right? We also describe on program counter. Yes, there's something here called the program counter. Right? If we observe here, there is something here called program counter. Before I go on to describe on the call, let me discuss on this program counter. Right. Remember your program when you load your program from your computer to your flash program memory in your board, on your board. So all those programs are stored in your flash program memory, starting with the address of 00, 00. All right. So the program counter is also a register by itself. Yes, I think. Let me see. The program counter. The program counter here is also a register, right? So I've not finished on the slide set on the program counter. So the program counter here is program counter here. Okay, the program counter here Right. It's something like your stack pointer also. It stores your address. But program counter stores the address of your current program, right? Remember your program is in is a lines of codes, and your the we call it every lines in your code, right, has an address. Every lines in your code has an address. For example, let me say this first. Let's say, for example, I'm doing something like add, for example, R1 to R2. Then I add, right, R3 to R4, something like this. So each one of these actually has this, all this is, we call it assembly language, right? So this is one line process in assembly language. And you should already know that your assembly language, when you compile, or when, what's the term, is if C, in C programming, you use the term compile, right? So this is also something like compiling, compiling. So when what it does in when it does the compiling is that it changes this instruction, right, into 16-bit 16-bit instruction code. For example, it becomes something. This is not an address. This is a hexa value. So this line of code will be changed into some we call it machine language, which consists of zeros and ones. Zeros and ones. So, and these zeros and ones, if we represent that as hexa, it can be something like 05, let's say FA, something like this, something like this. So when you compile, this is not address, it's not address. When you compile this instruction, your compiler or your assembler, when you compile means you compile from C into assembly language. Do you know, actually, when you do your C programming, right? Your computer is a machine. Your computer does not know what you call it. Does not know about printf or void. Does not know anything about that. So your computer only knows zeros and ones. Because in your computer is all logic circuits and ALU, things like that, right? So when you use the term, when you learn C programming, C programming, there's a term compile, right? You use a compile and then you execute, you make your program run. So when you compile, compile is a process of converting from C into assembly. So that's compiling. Compiling. So compile from C language into assembly language. All right, and then compile from C into assembly, and then it becomes like this, right? It becomes something like this. So this is your assembly language, and then you need to pass through this assembly language into an assembler. Just now it is a compiler, and then you need to pass to a process of assembler, right? So when you pass this code to an assembler, it will change. This is the computer still does not know this, does not know this. And assembler converts this. They call it. This is a low-level language, Some language that we can still understand because we use the word add, we use the word sub or move, things like that. So this one is still computer does not know what to do, right? But programmers do know. But this is a very low level programming. So low-level programming, programmers can do this lah, right? So compiler compiles from C language into assembly language using the compiler, and then you have another process called the assembler. So the assembler is going to convert this instruction through the architecture of the processor used in that machine. It will change into this you call it machine language, machine language. So this is this hex code, this hex values represents this instruction. All right. So what happens when you download your program from your Arduino IDE into your board? So your Arduino IDE does not actually send this all these words into your Arduino Uno. All right. Your computer, your program, Arduino IDE will convert when you click upload. So it will compile from this into this machine language, and then what does actually your computer your Arduino IDE send to your board? It actually sends this all this machine language to your flash program memory. It will send all this language into your flash program memory. So the first instruction, right, will be sent to the beginning of the address of the flash program memory. All right, and then the second instruction, right, will be sent also to the next address inside your flash program memory. So it might be something like CD, something like this lah. All right. So all your program will be here in the form of 16-bit, 16-bit instructions. Right? Machine language. Programmers, we do not know. So we need the assembler to convert from this low-level language or assembly language into this machine language. We need an assembler. The assembler is provided by the manufacturer lah. But actually, if you look at data sheets, we can actually create an assembler on our own. No problem. But why create new when there's already an assembler? So just use that. All right. So what happens here? So in the flash program memory, you have all your 16 bits, all your lines, 16-bit lines of your program for every line, for every line. So this program counter is something like your stack pointer. It is a pointer. It is also a pointer lah. All right. It points to the address of the current instruction. The program counter points to the address of your current instruction which you are executing, right? So that is the program counter. All right. So the thing is, let's say your program is running line by line over here, and then suddenly you call a subroutine or an interrupt happen. Interrupt happens. All right. So after or when you call your subroutine, all right, or let's say for example, let's stick to this story. So an interrupt happens. When you are doing your controller microprocessor are doing processing lines by line, and then suddenly an interrupt happen. All right. So we want that after finishing that interrupt, all right, we want to go back to the main program, but we need to know where is the last line, where is the last line of code that the main program left. All right, when the interrupt happened, right? So this is where you can see the purpose of the program counter. All right. So when an interrupt happens, so what you need to do, what is not what you need to do automatically. Automatically, the address of the recent line of code, the recent line of code is being stored into the stack pointer, right? It is being stored to the stack pointer, which is at the bottom here lah. So basically, when you call a subroutine or an interrupt happen, when an interrupt happen or a subroutine is called, all right. So the first thing before you do the push, right, and finally the pop, so before you do the push, automatically, actually, the microprocessor will store your program counter at the beginning. I mean, at the end of your step pointer. Right? It will store your program counter first. All right. Because why? After you finish all your program, right? When your program found, I mean, when your interrupt service routine end with RETI, so what will happen? It will return the address of your program counter, right? PC, it will return back to the control of your microprocessor, and then your microprocessor will know which address to continue from. Okay. Where do you continue from? Because suddenly just now you have the interrupt, right? And everything is you have already saved the address or where you stop. So when you finish the interrupt service routine, right? You want to go back, you want to continue, so you have the address where you want to continue from, right? So when you call the RET, right, the return address is popped back from the stack. This return address actually contain your program counter. So when you do your call of subroutine or when you have your interrupt, it is decremented by 2. Right? Why 2? Because it is a 16-bit, right? Because the program counter is 16-bit, right? So first thing, when you go into when an interrupt happen or when you call a subroutine, it will store to 8 bits or 16 bit, which contains your return address. Your return address is your program counter. Okay. Okay. So your return address is pushed back is pushed onto the stack when something happens or interrupt. So you do your process in your interrupt, things like that. And then when you finish that, you put a RET or RETI return, and then your step pointer will be incremented by 2. And at this point, your program counter or return address is popped, and passed and stored into the program counter here, right? It's stored here to be registered in the program counter here, and then your main program can continue lah, right? Because this holds the current, the program counter holds the current address, right, of the executing instruction, right? So this is how it happens lah. So please understand this. I might have questions later for you, right? So that would be on the stack pointer. Okay. Okay, I think that's it for this session today. We have discussed until stack pointer and also GPR. All right. So we'll continue our session, our next session on specifically program counter lah, program counter. So we will look if we to look at data sheets. So I arranged my slides according to your this data sheet lah. This data sheet. Right. So we have view APR here. So we have looked at this is on memories. Here, stack pointer. Stack pointer. So next session we will look at a little bit on the instruction execution timing, a little bit on reset, and we'll look. This is an assembly code example assembly code. All right. So if you look in the data sheet, this is on page 24. of this data sheet, 80 mega 328. Simplify this. Let's see. Okay. So we as engineers should be familiar lah. So this is what differentiates us from computer science. So computer science, they do only C code example. They only do C programming. For computer science, when you take the course computer science, you do high level language, HLL. But we as engineers, we also learn about high level language, right? But we go further. That's why we are engineers, right? So engineers are much heavier than computer science, because you'll be graduating as Bachelor of Engineering. So those computer science will be graduating as Bachelor of Science. So that will be very, very different, right? So we go deeper, right, into assembly language and then into logic digital circuits. You can see here, for example, this is almost the same representation between C programming, all right, and assembly code. So we can see here, for example, in there's an instruction in, you put R16 then SREC. So it says here store SREC value. So store this SREC value into R16. Right, and then CLI, remember the instruction CLI. So disable interrupts during time sequence. So we are disabling interrupt. And then it have a process of start EEPROM write. So SBI, EAMPE, and then EECR. These are registers also. We have not looked at that. We will see that further after this. So start EEPROM write and then restore SREC value. Right, I think so. This is something like this is part of the interrupt service routine actually. This is part of the program in an interrupt service routine. So inside the coding of the interrupt service routine, this is not the main code. So you store the value first in the SREC, in the main of SREC in the R16. Then you disable the interrupt, right? And you do some, in this case, during the interrupt, the programmer wants to write some or save some value or variables inside the EEPROM. Right, after finishing that, after finishing the process, it restores the value. So it restores back. So out and then SREC back into R16. So disable interrupt and then do the process. So for the call it similar C programming. So it's this. So you need to declare a variable. This is declared as a character. C SREC as a character C here. C what variable? SREC variable. And then just equate here. C SREC equals to SREC. Because why you need to store or save this value? Because in this process, build after this, okay, the SREC might be might change, but in this case, during all these changes in this process here, from right here, and then the SREC will have many changes, and after that you want to restore back because you want to continue, right, with the value of SREC before this process over here, right? So so you store, and then you restore back. So this is how you write CLI in C. All right, and then this is how you write the SBI over here. Is similar to the instruction here, right? And then this section over here is similar to this section over here, right? And then finally here, you restore back. So it's the other way around. S right is equals to C S right. C S right is the character that you create the variable, right? So the thing is, when you do the C, you don't write specifically to which R, which GPR. So if you use assembly language, you can assign specifically which this is R16 means your GPR. Remember your general purpose register over here. Yeah, R16 here. So this is your GPR or general purpose registers. So, but when you do C, you don't have the the exclusivity or you don't have the control to choose which general purpose register that you want to use. So in this case, the C compiler will select uh, any registers which is empty, for example. All right, so you can see here the C assembly language and the related C coding example. So remember for your CDIO, all right, like I said, you cannot use Arduino. Arduino, you cannot use Arduino board, and you also cannot use the Arduino IDE. IDE. So you're going to, if you have read on the specifications for the CDIO, you're going to use the software Artemis Studio 7. Artemis Studio 7. You're going to use this type of C. This type of C, you cannot use this in the Arduino Uno. Arduino Uno. I mean, you can use this on the Arduino IDE. So you need to use another platform. So this is not the C which is used in your Arduino IDE. That would be different. Different. All right. Okay, and then we're going to look at this is also another example over here. SEI, and then there's a sleep function. So set global interrupt, right? Set, and then you can go to sleep. So enable interrupt. So this is how you do the SEI in C, set global interrupt, and this is how you're going right the function sleep. Sleep. So enter sleep. Right. So after that, we're going to discuss on the memories, the memories inside the 80 mega. So that will be on the next session. All right. So yeah. Okay. Thank you, everyone. Thank you for attending. All right. You can also look again, look back at this session with the given address, which I will share with you later. All right. Thank you, everyone. Goodbye.
Doctor,
Yeah.
can we have the lecture note that you used for this class?
Which one?
Can we have the lecture notes that you
Oh,
used?
these slides.
Yeah.
Okay.
Okay, Doctor.
Thank you, Doctor.
Okay. Welcome.
Thank you, Doctor.
Okay.
Doktor,
Saya.
Doktor saya ada soalan jap. Sikit.
Uh-huh.
Saya nak tanya yang berkenaan dengan